The fabric of space-time. Black holes and gravitational waves. Until recently, astronomy was limited to light. For centuries, telescopes expanded our view of the cosmos, stretching from Galileo's tiny refractor to Hubble's deep fields and Webb's infrared vision. But light alone cannot tell the full story of the universe. There are events so violent, so enshrouded in dust and energy, that no photon can escape. For those phenomena, we needed a new messenger. That messenger is the gravitational wave. Predicted by Einstein in 1916 as ripples in the fabric of space-time, gravitational waves eluded direct detection for a century. Their effect is absurdly small, stretching and squeezing space-time by less than the width of a proton across kilometers. For decades, they seemed undetectable in practice, a beautiful prediction with no hope of verification. Yet by 2015, advances in laser interferometry, seismic isolation, and computational modeling converged. On September 14th of that year, the twin LIGO detectors in Hanford and Livingston recorded a chirp, a signal rising in frequency and amplitude before cutting off abruptly. It was the sound of two black holes, 36 and 29 solar masses, merging 1.3 billion light-years away. That first detection changed astronomy forever. It was not just a triumph of technology. It was a new sense added to humanity's perception. For the first time, we could listen to the universe as well as see it. LIGO and its partner observatories, Virgo in Italy and Cagra in Japan, have since built a catalogue of dozens of black hole mergers, neutron star collisions, and mysterious compact object events. Each detection has reshaped our understanding of the populations of black holes and neutron stars, and opened questions no one had thought to ask before. Black holes in the 21st century. The rise of gravitational wave astronomy coincides with another revolution, the direct imaging of black holes. In 2019, the Event Horizon Telescope unveiled the first image of a black hole's shadow in M87 star, a supermassive giant with 6.5 billion solar masses. The orange ring, synchrotron radiation from hot plasma orbiting at near-light speeds, encircled a dark void where no light could escape. In 2022, the EHT delivered a second historic image, this time of Sagittarius, a star, the 4.3 million solar mass black hole at the center of our own Milky Way. These images provided visual confirmation of what gravitational waves had proven dynamically. Black holes are not abstractions of mathematics, but physical objects sculpting space-time. They confirmed the predictions of general relativity to within a few percent. Yet they also opened new puzzles. How do jets extending thousands of light-years form from regions smaller than our solar system? What role do magnetic fields play in launching them? Why do some black holes shine brilliantly as quasars while others remain dark? Together, gravitational waves and horizon-scale imaging provide complementary views. One measures the dance and merger of compact objects, the other their static silhouettes. Both are now advancing hand in hand, supported by numerical relativity simulations that can turn equations into waveforms and interferometers that can measure distortions smaller than atoms. The LIGO- Virgo-K AGRA catalogue. Since the first detection in 2015, LIGO and Virgo have compiled a catalogue of gravitational wave events that has transformed black hole astrophysics. By the end of their third observing run, 03 in 2020, they had identified nearly 90 candidate events. These include binary black hole mergers ranging from 5 to over 80 solar masses, the famous neutron star merger GW 170817, accompanied by electromagnetic counterparts across the spectrum, exotic systems like GW 190521, a merger of black holes in the pair instability mass gap, too heavy to form from ordinary stellar collapse. Each event carries unique information. By analyzing the chirp's frequency and amplitude evolution, astronomers extract the masses and spins of the merging black holes. Population studies suggest that many black holes are heavier than expected from stellar models, pointing to low metallicity progenitors or hierarchical mergers. Spin measurements hint at multiple formation channels, with some binaries forming in isolation and others dynamically in dense stellar clusters. The neutron star merger, GW 170817, was a watershed moment. Not only did it produce gravitational waves, it also triggered gamma-ray bursts, kilonova optical light, and radio afterglows. For the first time, astronomers observed the same event in both gravitational and electromagnetic waves, a true multi-messenger detection. That event confirmed that neutron star mergers forge heavy elements like gold and platinum, solving a decades-old mystery of nucleosynthesis. The promise of LISA. While LIGO, Virgo, and KAGRA detect high-frequency gravitational waves from stellar mass black holes and neutron stars, the upcoming Laser Interferometer Space Antenna, LISA, will open the low-frequency frontier. Scheduled for the 2030s, LISA will consist of 3 spacecraft in a triangular formation millions of kilometers apart, trailing Earth around the Sun. LISA will detect mergers of supermassive black holes at the centers of galaxies, extreme mass ratio inspirals, where a stellar mass black hole spirals into a giant, and possibly signals from exotic sources like cosmic strings. Unlike ground-based detectors, LISA will observe inspirals for months or years, providing precise measurements of masses, spins, and orbital parameters. These observations will reveal how galaxies and their central black holes co-evolved, and test general relativity in regimes far beyond current experiments. The synergy between LIGO and LISA will be profound. Together, they will span 8 orders of magnitude in frequency, covering everything from stellar remnants to the giants shaping galaxies. The coming decades promise not just more detections, but a complete gravitational wave spectrum of the universe. Black holes as laboratories of fundamental physics. Black holes are not just astrophysical objects. They are laboratories for fundamental physics. Their horizons test the limits of general relativity, quantum mechanics, and thermodynamics. Gravitational wave detections allow us to measure whether the ring-down frequencies of merging black holes match Einstein's predictions. So far they do, but future detections with higher signal-to-noise ratios may reveal subtle deviations. The information paradox remains one of the deepest unsolved problems in physics. If black holes evaporate via Hawking radiation, what happens to the information encoded in the matter that fell in? Do quantum effects modify the horizon? Gravitational wave echoes, faint, repeating signals after a merger, have been proposed as signatures of new physics, though none have yet been confirmed. Some theories even suggest that primordial black holes could make up part of dark matter. If Webb or Euclid detects microlensing signatures consistent with small black holes, and if gravitational wave observatories detect mergers of objects with no stellar origin, this hypothesis could gain traction. Black holes thus link cosmology to quantum gravity, acting as cosmic testbeds for ideas that no Earth-based experiment could probe. The story of black holes and gravitational waves is only beginning. LIGO and Virgo are currently undergoing upgrades for the O4 and O5 observing runs, which will increase their sensitivity and detection rates. Hundreds of mergers per year may soon become routine. KAGRA in Japan, with cryogenic mirrors deep underground, will join the network fully, improving localization of sources. Meanwhile, the Event Horizon Telescope is refining its images with additional stations, aiming for movies of accretion flows around Sagittarius A star. New X-ray observatories like Athena and next-generation radio arrays like the SKA will study jets and feedback. And LISA, when launched, will complete the picture, adding supermassive black holes to the gravitational wave zoo. Black holes, once dismissed as mathematical curiosities, are now at the center of astrophysics. Gravitational waves, once thought impossible to detect, are now routine. Together, they have given us not just new data, but a new way of doing astronomy. We are no longer limited to light. We are listening to the universe, and what we hear is stranger and richer than we ever imagined. Neutron stars and the kilonova revolution. If black holes are the silent devourers of the cosmos, neutron stars are their more talkative cousins. Born in the violent deaths of massive stars, neutron stars are extreme objects, city-sized spheres only 20 kilometers across, packing more mass than the Sun into a crust of nuclear density matter. For decades, they revealed themselves primarily as pulsars, flashing beams of radio light with clock-like regularity. But their most dramatic act came in August 2017, with GW 170817, the first neutron star merger detected in both gravitational waves and light. The signal began as a low-frequency chirp in LIGO and Virgo, rising in pitch over 100 seconds before terminating in a merger. Within 2 seconds, NASA's Fermi telescope detected a short gamma-ray burst. Hours later, optical telescopes spotted a transient in the galaxy NGC 4993, glowing blue then fading to red over days. This was a kilonova, the radioactive glow of freshly forged heavy elements. For the first time, astronomers saw where gold and platinum come from. Not from the slow cooking of stars, but from the catastrophic collision of neutron stars. Follow-up observations across the spectrum, from X-rays to radio, tracked the expanding ejecta. Modeling showed that up to 0.05 solar masses of R-process material had been synthesized in the event, enough to seed thousands of Earths with precious metals. This single detection solved a mystery that had lingered since the 1950s, when nuclear physicists first asked where the heaviest elements were made. It also cemented the power of multi-messenger astronomy. By combining gravitational waves with photons, astronomers unlocked a chapter of cosmic alchemy invisible to either messenger alone: the nuclear physics of neutron stars. Gravitational waves from neutron star mergers do more than prove element synthesis. They encode the physics of matter at densities unreachable on Earth. The tidal deformation of neutron stars during inspiral depends on the equation of state, EOS, of nuclear matter. How neutrons behave when squeezed beyond the densities of atomic nuclei. By measuring the phase evolution of the GW 170817 signal, LIGO and Virgo placed constraints on the tidal deformability parameter lambda. This ruled out the stiffest equations of state, suggesting neutron stars are more compressible than some models predicted. Subsequent events, including possible neutron star black hole mergers, have tightened these bounds. Future detectors will do even better. The planned Einstein telescope in Europe and Cosmic Explorer in the US will have 10 times the sensitivity of LIGO, enabling precise measurements of many neutron star mergers. These observations will directly probe the behavior of matter at supranuclear densities, complementing experiments in particle accelerators like FAIR and RHIC. In effect, neutron stars are laboratories of quantum chromodynamics, their interiors governed by the strong nuclear force, in a regime inaccessible to terrestrial experiments. Population studies, a new black hole census. One of the surprises of gravitational wave astronomy is the diversity of black hole masses. Before 2015, most known stellar mass black holes weighed 5 to 20 solar masses, inferred from X-ray binaries. LIGO and Virgo however, detected mergers involving black holes of 30, 40, even 80 solar masses. Some, like GW190521, involved black holes so massive they fell into the pair instability gap, where stellar evolution theory predicted no remnants should exist. How do such black holes form? Several channels are now considered. One is stellar collapse in low metallicity environments, where weaker winds allow massive stars to retain more mass. Another is hierarchical mergers in dense star clusters, where black holes merge repeatedly, building up to higher masses. Population studies suggest that both channels may operate, as spin orientations differ between isolated binaries and dynamically formed ones. The diversity extends to spins as well. Some black holes spin rapidly, others barely at all. Some binaries show aligned spins, others misaligned, hinting at different evolutionary histories. By compiling catalogues of dozens and soon hundreds of mergers, gravitational wave astronomers are building the first empirical census of black hole populations, providing a reality check on decades of theory. Gravitational waves as cosmic rulers. Beyond astrophysics, gravitational waves are emerging as tools for cosmology. Binary mergers act as standard sirens. Their waveforms encode the absolute luminosity distance to the source. If the redshift can be measured independently, the Hubble constant can be determined directly, without reliance on distance ladders. GW170817 provided the first such measurement, albeit with large uncertainties. By combining the gravitational wave distance with the redshift of its host galaxy, NGC 4993, astronomers derived a value for the Hubble constant, consistent with other methods. As more events with electromagnetic counterparts are detected, these measurements will improve, potentially resolving the tension between early and late universe values of the Hubble constant. Even without counterparts, statistical methods can match gravitational wave events to galaxy catalogues, offering another path to cosmology. Future detectors like Cosmic Explorer and LISA will extend this method across redshifts, turning gravitational waves into independent probes of cosmic expansion. In time, they may even constrain dark energy, testing whether the acceleration of the universe is constant or evolving. Exotic sources and surprises. The first decade of gravitational wave astronomy has already produced surprises, and more are likely. Some events involve objects that blur the boundary between neutron stars and black holes, with masses in the so-called mass gap, around 2 to 5 solar masses. Are these heavy neutron stars, light black holes, or something more exotic? There are also tantalizing hints of eccentric mergers, which could signal dynamical formation in dense clusters. LIGO and Virgo have searched for continuous waves from rapidly spinning neutron stars, though none have yet been detected. Burst signals from supernovae remain a target, as do stochastic backgrounds from unresolved populations of binaries. More speculative possibilities include cosmic strings, hypothetical defects from the early universe that could emit bursts of gravitational waves, and even relic gravitational waves from inflation. While none have been detected, the expanding reach of detectors makes the coming decades fertile ground for discovery. The human side of the discovery. The detection of gravitational waves is also a human story. Thousands of scientists across continents contributed to LIGO and Virgo, building instruments sensitive to distortions smaller than an atomic nucleus. The engineering challenges were immense, isolating mirrors from seismic noise, stabilizing lasers to exquisite precision, and analyzing data with supercomputers. The triumph of 2015 was as much a victory of persistence and collaboration as of theory. The Nobel Prize in Physics in 2017 recognized Rainer Weiss, Kip Thorne, and Barry Barish for their leadership. But the achievement belonged to an entire community. Young scientists who joined LIGO in the early 2000s, as graduate students, found themselves authors of a discovery that reshaped astronomy. The collaboration model, vast, distributed, open in data sharing, set a precedent for big science in the 21st century. Gravitational wave astronomy is still young, and its practitioners are still expanding the network. India's LIGO India project will add another detector in the next decade, improving source localization. The global effort ensures that this new window on the universe will remain open and expanding for generations. Black hole neutron star mergers. In 2021, LIGO and Virgo announced the first unambiguous detections of black hole neutron star mergers, GW 200105 and GW 200115. Each involved a neutron star being swallowed by a black hole tens of solar masses in size. Unlike neutron star collisions, no bright kilonova was observed. In both cases, the black hole appears to have consumed the neutron star whole, leaving little ejecta. These events are valuable because they probe the frontier between compact objects. They show that binary evolution channels can produce mixed pairs, and that such systems are not vanishingly rare. In some cases, if the black hole is smaller or the neutron star more massive, tidal disruption could produce electromagnetic signals, perhaps even kilonova-like ejecta. Such a detection would provide a new laboratory for studying matter under extreme conditions, and a new way to test whether neutron star interiors behave as expected. Future observing runs will expand this sample. By comparing rates of black hole neutron star mergers to those of double neutron star and double black hole systems, astronomers can constrain binary formation pathways. Do such systems form primarily from isolated stellar binaries, or dynamically in dense stellar clusters? Each new detection adds a piece to the puzzle of how massive stars live and die. The stochastic gravitational wave background. Beyond individual events, gravitational wave detectors are also sensitive to a faint background, the superposition of countless unresolved signals. This stochastic background is expected to arise from billions of distant binary mergers, too faint to detect individually. Like the cosmic microwave background for light, it represents a diffuse glow of gravitational energy across the universe. In 2023, pulsar timing arrays, networks of millisecond pulsars monitored with exquisite precision, announced evidence for a low-frequency gravitational wave background. The signal appears as correlated deviations in the arrival times of pulses across the sky, consistent with a background from supermassive black hole binaries. This is the first detection of gravitational waves in the nanohertz regime, opening a new frequency window. Ground-based interferometers, like LIGO, are also searching for a higher frequency stochastic background. If detected, it would provide direct insight into the history of compact object mergers. More speculative contributions could come from phase transitions in the early universe, cosmic strings, or other exotic physics. The stochastic background is not just noise. It is a record of the universe's deepest processes, waiting to be decoded. Primordial black holes. Relics of the Big Bang. Among the most intriguing possibilities raised by gravitational wave detections is the existence of primordial black holes. Objects form not from stars but from density fluctuations in the early universe. If inflation produced regions of enhanced density, they could have collapsed directly into black holes, only fractions of a second after the Big Bang. Primordial black holes could, in principle, span a vast range of masses. The smallest would have evaporated via Hawking radiation by now, but those of stellar mass or larger could survive. Some theories even propose that primordial black holes could account for part of dark matter. Gravitational wave observations offer a test. If LIGO detects black hole mergers with properties inconsistent with stellar origins, for example, unusually low spins or masses in the 1 to 3 solar mass gap, they could be primordial candidates. The discovery of black holes around 30 solar masses, heavier than expected from many stellar channels, has fueled speculation. While no event has yet provided conclusive proof, the door remains open. Future surveys, both gravitational and electromagnetic, will tighten constraints. Microlensing surveys like OGLE and Euclid can search for primordial black holes via their gravitational influence on starlight. If confirmed, primordial black holes would not only solve the mystery of dark matter, but also provide a direct window into conditions milliseconds after the Big Bang. Gravitational waves and the nature of dark matter. Dark matter remains one of the greatest mysteries in science. Gravitational waves offer several indirect routes to probing its nature. One is through primordial black holes, as mentioned. Another is through how dark matter halos influence the dynamics of compact binaries. If black holes spiral inside dense dark matter environments, they may experience dynamical friction, altering the gravitational waveform in subtle ways. Another possibility lies in axion clouds. Some theories propose that ultralight bosons, candidates for dark matter, can form clouds around spinning black holes via a process called superradiance. These clouds could emit continuous gravitational waves or affect black hole spin distributions. So far, no evidence has been found, but future detectors may be sensitive enough to test these predictions. The stochastic background could also contain signatures of dark matter physics. If dark matter underwent phase transitions in the early universe, it could have generated gravitational waves detectable today. LISA and other space-based detectors may be able to test these scenarios directly. In this way, gravitational waves complement traditional dark matter searches, probing phenomena invisible to light or particles. Testing general relativity with black holes. Every gravitational wave detection is also a test of Einstein's general relativity. By comparing observed waveforms to theoretical predictions, scientists can check whether gravity behaves as expected in the strong field regime. So far, general relativity has passed every test, with no deviations detected. But the precision is improving. The ring-down phase of black hole mergers, when the final black hole settles into equilibrium, provides especially clean tests. The frequencies of these oscillations depend only on the black hole's mass and spin, a prediction known as the no-hair theorem. If additional modes are detected that cannot be explained by general relativity, they could signal new physics. Similarly, searches for echoes in the post-merger signal aim to test whether horizons are truly event horizons or if exotic structures like gravastars exist. While no echoes have been confirmed, the possibility keeps theorists intrigued. Each new event with high signal-to-noise ratio pushes the limits of our ability to test gravity, turning black holes into laboratories of fundamental physics. Gravitational waves and the early universe. Perhaps the most ambitious goal of gravitational wave astronomy is to probe the universe's earliest moments. Unlike photons, which decouple only after 380,000 years, gravitational waves interact so weakly that they could carry information from the first fractions of a second. Relic gravitational waves from inflation could provide direct evidence of that epoch, revealing the energy scale of the universe's birth. Current detectors are not sensitive enough to detect such relics. But future space-based missions may be. The search overlaps with efforts in cosmic microwave background polarization, where B-mode patterns may carry imprints of inflationary gravitational waves. Together, these approaches aim to probe the universe's origin directly, a quest once confined to theory. In this sense, gravitational waves are not just about compact objects. They are a new messenger of cosmic history, carrying information inaccessible to any other method. If detected, primordial gravitational waves would revolutionize cosmology, providing a direct window into physics at energies trillions of times higher than any particle accelerator. Magnetars and the search for continuous waves. Not all gravitational waves come in brief, spectacular bursts. Some could be steady whispers, emitted continuously over years. Rapidly rotating neutron stars, particularly magnetars, whose magnetic fields are 1,000 trillion times stronger than Earth's, are prime candidates for such signals. If a neutron star's shape is even slightly asymmetric, its rotation should radiate gravitational waves at twice the spin frequency. LIGO and Virgo have conducted deep searches for continuous waves from known pulsars, especially the Crab and Vela pulsars, but so far no detections have been made. The limits, however, are scientifically valuable. They tell us that these neutron stars are astonishingly round, deformed by less than a fraction of a millimeter. Magnetars, with their violent starquakes and flares, remain promising. A sudden crack in the crust or rearrangement of magnetic stresses could briefly amplify gravitational wave emission, perhaps detectable in the next generation of detectors. If continuous waves are found, they will act as seismology for neutron stars, revealing their internal structure and the properties of nuclear matter. They would also provide natural laboratories for testing theories of superfluidity and superconductivity under conditions impossible to reproduce on Earth. Cosmic Explorer and the Einstein Telescope. The next leap for ground-based detectors will come with third-generation observatories. The US-based Cosmic Explorer, with 40-kilometer arms, and Europe's Einstein Telescope, a triangular underground facility with cryogenic mirrors, aim for sensitivity 10 times better than advanced LIGO. This leap will transform gravitational wave astronomy. Instead of dozens of events per year, thousands will be detected. Neutron star mergers will be visible to redshifts of 2 or more, enabling population studies across cosmic history. Black hole mergers will be routine, providing precise mass and spin distributions. For the first time, continuous waves from neutron stars may become detectable. Perhaps most importantly, third-generation detectors will measure black hole ringdowns with such precision that subtle deviations from general relativity could be spotted. They will also vastly improve standard siren cosmology, allowing the Hubble constant to be measured with percent-level accuracy. In short, they will move gravitational waves from discovery to precision science, as Hubble did for optical astronomy. Multi-messenger synergy. One of the greatest strengths of gravitational wave astronomy is its synergy with other messengers. GW 170817 proved this beyond doubt, but the principle extends further. Gamma-ray bursts, X-ray afterglows, optical kilonovae, and radio jets all provide complementary information to gravitational waves. By combining them, astronomers can reconstruct events in full detail, from inspiral to explosion to afterglow. Neutrinos are the next frontier. A neutron star merger or a collapsing massive star could produce a burst of neutrinos detectable in giant underground observatories like IceCube or Hyperchemiocande. If correlated with gravitational waves, such detections would provide a complete picture of compact object physics. In this sense, the 21st century is not just about multi-wavelength astronomy, but truly multi-messenger astronomy, with photons, gravitational waves, neutrinos, and even cosmic rays all contributing. Black hole feedback and galaxy evolution. Black holes are not isolated players. They shape galaxies themselves. Supermassive black holes at the centers of galaxies regulate star formation through jets and winds, a process known as feedback. Gravitational waves now add a new dimension to this picture. By detecting the mergers of supermassive black holes with LISA, astronomers will be able to trace how galaxies grew through collisions and how their central engines coalesced. Simulations show that black hole mergers can shake entire galaxies, ejecting stars and triggering bursts of star formation. The gravitational recoil from asymmetric wave emission may even kick black holes out of their host galaxies, leaving behind wandering giants in intergalactic space. Detecting such events would prove that feedback operates not just through radiation and jets, but through gravity itself, altering the destiny of galaxies, the stochastic symphony of the universe. As detectors grow more sensitive, the stochastic background will move from speculation to measurement. Already, pulsar timing arrays hint at the low-frequency symphony of supermassive black hole binaries. In the coming decades, LISA will resolve many of these systems individually, while third-generation ground-based detectors will measure the higher frequency background from stellar mass binaries. What will this background sound like? It will be a hum, rising and falling across frequencies, encoding the entire history of structure formation. Each merger adds its note, and together they form a cosmic symphony. Detecting and characterizing this background will provide statistical information on populations too faint to detect directly, completing the census of compact objects across time. Exotic physics at the horizon. While black holes so far obey Einstein's equations, theorists continue to explore alternatives. Could horizons be replaced by exotic structures like fuzzballs or gravastars? Could extra dimensions modify gravity at strong scales? Could quantum effects alter the ring-down spectrum? Gravitational waves are the key to testing these ideas. If echoes appear after a merger, they may indicate a surface just outside the horizon. If ring-down frequencies deviate from predictions, they could point to new physics. So far, no evidence has been found, but future detectors may change that. Even the absence of deviations is valuable. Every confirmation of general relativity in the strong field regime strengthens our confidence in the theory, while narrowing the space for alternatives. In this way, black holes act as cosmic truth machines, telling us whether our deepest theories hold. Listening to the universe. Ultimately, gravitational wave astronomy is about expanding our senses. For millennia, humans saw only with their eyes. The invention of the telescope extended that vision to the stars, then across the spectrum from radio to gamma rays. Now, for the first time, we can listen as well. The universe is alive with sound, the chirp of merging black holes, the bass of supermassive inspirals, the hiss of the stochastic background. Each detection is not just a data point, but a new voice in the cosmic chorus. As detectors grow, the music will become richer, filling in harmonies we cannot yet imagine. This change is not only scientific, but philosophical. To listen to space-time itself is to realize that the universe is not silent, but vibrating with the echoes of creation and destruction. It is to recognize that gravity, the oldest force, speaks in waves we have only just learned to hear. LISA and the low-frequency frontier. The launch of the Laser Interferometer Space Antenna, LISA, in the 2030s will mark the dawn of a new era. Unlike LIGO and Virgo, which listen for fleeting chirps from stellar mass objects, LISA will eavesdrop on the deep bass notes of the universe. Its 3 spacecraft, flying in a triangular formation millions of kilometers apart, will form an interferometer sensitive to gravitational waves, with periods of minutes to hours. LISA will be tuned to detect the mergers of supermassive black holes, ranging from 100,000 to 1 billion solar masses. Such mergers, triggered by galaxy collisions, shape the growth of structure on cosmic scales. The gravitational wave signals will last for months, their gradual inspirals tracked with extraordinary precision. By the time the final plunge occurs, astronomers will know the masses, spins, and orbits with accuracy unmatched in astrophysics. The promise goes beyond individual events, because LISA can detect sources out to redshifts of 20. It will map the coevolution of galaxies and their central black holes across most of cosmic history. It will also test general relativity in the most extreme regime imaginable. The merger of horizons billions of kilometers across. LISA will not just complement ground-based detectors, it will expand the gravitational wave spectrum by a factor of 1,000,000 in frequency, uniting the universe's deepest base with its highest treble. Extreme mass ratio inspirals, the precision probes. Among the most anticipated sources for LISA are extreme mass ratio inspirals, MRIs, in which a stellar mass black hole, neutron star or white dwarf, spirals into a supermassive black hole. These inspirals produce gravitational waves that encode the geometry of spacetime around the giant with exquisite detail. Imagine a 10 solar mass black hole orbiting Sagittarius, a star for thousands of loops, before plunging into the horizon. Each orbit distorts spacetime in a slightly different way, producing a gravitational waveform that acts like a map of the black hole's metric. By analyzing MRIs, LISA will test whether real black holes obey the Kerr solution of general relativity, or whether subtle deviations exist. The information yield is staggering. MRIs will allow astronomers to measure black hole spins with 1 part in a million, to detect quadrupole moments inconsistent with relativity, and to trace stellar populations in galactic centers. They are not just exotic events, they are precision experiments, using nature's most extreme laboratories to test the foundations of physics. Gravitational waves as high-redshift cosmology tools. The use of gravitational waves as standard sirens is poised to transform cosmology. Each binary merger provides a direct measurement of distance, independent of cosmic ladders like Cepheids or supernovae. With hundreds or thousands of such events, astronomers will be able to chart the expansion of the universe across time. Ground-based detectors already provide distances out to Z, approximately 2 for black hole mergers, and Z approximately 0.1 for neutron star mergers. LISA will extend this to Z till 20, probing the expansion of the universe during epochs previously unreachable. Combined with redshift measurements from electromagnetic counterparts or statistical associations, this will produce an independent Hubble diagram spanning nearly the entire history of the cosmos. The stakes are high. Current measurements of the Hubble constant disagree. Local Cepheid and supernova methods yield a higher value than CMB-based inferences from Planck. Gravitational waves could adjudicate this Hubble tension. If they agree with one side, the other must revisit its assumptions. If they fall in between, new physics may be required, perhaps involving dark energy or modified gravity. In either case, gravitational waves will provide clarity where light alone has reached an impasse. The hunt for exotic compact objects. Gravitational waves also provide a testbed for objects beyond black holes and neutron stars. Some theories of fundamental physics predict exotic compact objects, boson stars, gravastars, or other horizonless entities. These would mimic black holes, in many ways, but deviate in their gravitational signatures. The inspiral of such objects could produce waveforms with subtle differences in frequency evolution. Their mergers might lack the clean ring-down expected from black holes. Post-merger echoes could appear if horizons are replaced by reflective surfaces. So far, no compelling evidence has emerged, but detectors are only beginning to reach the required sensitivity. The discovery of even one exotic compact object would be revolutionary, proving that nature allows solutions stranger than Kerr black holes. Conversely, the absence of deviations after hundreds of detections will strengthen the case that black holes are exactly what Einstein predicted, spacetime wrapped so tightly that no escape is possible. Cosmic memory, the permanent imprint of waves. One of the strangest predictions of general relativity is the memory effect. After a strong burst of gravitational waves passes, space-time itself remains permanently displaced. Two test particles initially at rest will find themselves subtly shifted apart after the wave has gone. This permanent scar is unlike anything in electromagnetic radiation, where fields oscillate but return to baseline. Detecting memory would be a triumph. It requires exquisite sensitivity, as the displacements are minuscule. Pulsar timing arrays may be the best hope, as the long-term deviations in pulse arrival times could reveal memory from supermassive black hole mergers. If confirmed, memory would not only validate yet another prediction of relativity, but also provide insight into the non-linear nature of gravitational waves. The philosophy of space-time as a medium. Gravitational waves remind us that space-time is not an inert stage, but a dynamic participant in the cosmos. When two black holes merge, they do not merely disturb their surroundings. They send ripples through the very fabric of reality. These ripples stretch and squeeze distances, altering the geometry of the universe itself. Philosophically, this is profound. Newton saw space and time as absolutes, a static arena in which matter moved. Einstein showed that space and time were flexible, shaped by matter and energy. Gravitational waves take this further. Space-time can not only curve, but also oscillate, vibrate, and carry energy. The medium of existence is active, not passive. Listening to gravitational waves is, in a sense, listening to the heartbeat of the universe. Each chirp is a pulse of space-time, a direct expression of the dynamism of reality. It forces us to reconsider what it means to say that something exists. Space-time is not emptiness, but structure, capable of motion, memory, and communication. Toward a complete gravitational universe. As we combine ground-based detectors, space-based interferometers, pulsar timing arrays, and theoretical models, a vision emerges of a complete gravitational universe. High-frequency chirps from stellar mass black holes, low-frequency hums from supermassive binaries, continuous whispers from neutron stars, and stochastic rumbles from the cosmic background. All form a spectrum as rich as light's electromagnetic counterpart. This gravitational spectrum will eventually be as familiar to astronomers as the radio to gamma ray spectrum is today. Each band probes different phenomena, from star deaths to galaxy growth, to the birth of the universe itself. In the 21st century, gravitational astronomy is moving from novelty to necessity, as indispensable as telescopes or satellites. The fabric speaks. The fabric of space-time speaks, and we have begun to understand its language. Its vocabulary includes chirps, hums, and echoes. Its grammar is the mathematics of general relativity. Its stories are those of creation and destruction, black holes colliding, neutron stars dissolving, galaxies coalescing. Every detection expands the lexicon. What began with a single chirp in 2015 has grown into a symphony, and soon into a full orchestra. To master this language is to read the autobiography of the cosmos, written not in light, but in waves of gravity. The growing black hole menagerie. With every new detection, the catalogue of black holes grows stranger. LIGO's early discoveries already revealed heavier black holes than expected, hinting at low metallicity progenitors. Later events suggested entire subpopulations, binaries with aligned spins pointing to isolated stellar evolution, and others with random orientations pointing to dynamical assembly in globular clusters or galactic nuclei. There are black holes in the so-called mass gap, neither light enough to be neutron stars, nor heavy enough to be predicted by standard stellar collapse. There are mergers so asymmetric that one object may have been 3 times the mass of the other, raising questions about capture scenarios. As this menagerie expands, we begin to see black holes not as uniform products of stellar death, but as a diverse ecosystem. Some are relics of massive primordial stars. Some are the results of repeated mergers in star clusters. Some may even trace their origins to the earliest epochs of the universe. The richness of this census will only grow as third-generation detectors come online, turning what is now a few dozen detections into hundreds of thousands. Black holes as engines of galaxy evolution. Black holes are not just astrophysical curiosities, but central players in the cosmic story. Supermassive black holes, weighing millions to billions of solar masses, reside in the hearts of nearly all galaxies. Their growth and activity regulate star formation on galactic scales. Jets launched from accretion disks heat interstellar gas, preventing runaway starbursts. Winds driven by accretion outflows can strip galaxies of their fuel. Gravitational waves allow us to trace how these giants formed. When galaxies merge, their central black holes sink toward the center and eventually collide, releasing gravitational waves powerful enough to outshine the electromagnetic universe. LISA will detect such mergers across billions of light-years, providing the missing link between galaxy evolution and black hole growth. In this way, black holes cease to be footnotes and instead become the engines around which galactic history revolves. The role of star clusters and nuclear environments. Not all black hole binaries form in isolation. In dense star clusters, black holes sink to the center, interact gravitationally, and frequently form new binaries. These binaries can be ejected by three-body encounters, merge in isolation, or spiral together while still bound to the cluster. The high masses and random spin orientations of many LIGO events support this dynamical channel. Galactic nuclei provide another crucible. Around supermassive black holes, stellar densities are extreme, and gas disks may shepherd black holes into orbits that enhance merger rates. Some models predict a population of black holes in active galactic nuclei disks, detectable through their unique eccentric waveforms. Gravitational wave observations thus provide not only stellar, but also galactic archaeology, revealing the environments where black holes live and die. Gravitational waves and time-domain astronomy. We are living in an age when astronomy has become time-domain driven. Telescopes scan the sky nightly for supernovae, gamma-ray bursts, and transient phenomena. Gravitational waves fit naturally into this landscape, providing alerts that trigger telescopes worldwide. When LIGO announces a candidate event, networks of optical, radio, and X-ray observatories scramble to search the patch of sky for counterparts. The success of GW 170817 proved the value of this coordination, but the process is far from trivial. Localizing a gravitational wave event requires triangulation across detectors. And early in LIGO's history, error regions were hundreds of square degrees. With more detectors online, these regions shrink, but challenges remain. As sensitivity grows, alerts will come weekly or daily, overwhelming follow-up resources. Astronomers are building automated pipelines and prioritization strategies to decide which events to chase. The fusion of gravitational and electromagnetic astronomy will require not just instruments, but global cooperation and strategy. The frontier of precision tests. With each detection, the precision of general relativity tests improves. The inspiral phases test the propagation speed of gravitational waves, already confirmed to match light's speed to better than 1 part in 10 to the power of 15. The merger phases test whether horizons behave as predicted, with ring-down frequencies matching the Kerr solution. The absence of dispersion places tight constraints on theories, with massive gravitons, or modified gravity. Future detectors will push these tests further. Cosmic Explorer and the Einstein telescope will detect signals with signal-to-noise ratios in the hundreds, allowing multiple ring-down modes to be resolved. LISA will map spacetime around supermassive black holes, with precision rivaling laboratory experiments. Each test so far confirms Einstein, but the true prize would be a deviation. Even a small one could signal new physics, perhaps quantum gravity or extra dimensions. The promise of gravitational waves is not only that they confirm, but that they challenge, forcing our deepest theories into the crucible of observation. The cultural impact of gravitational waves. The discovery of gravitational waves is not only scientific, but cultural. In 2015, when LIGO first announced detection, headlines around the world declared the confirmation of Einstein's last prediction. The signal, a tiny chirp lasting less than a second, was shared millions of times, turned into sound files, and even remixed into music. It symbolized humanity's ability to perceive the imperceptible, to extend our senses into the fabric of reality itself. Like the first image of Earth from space, or the first steps on the moon, gravitational waves resonate beyond laboratories. They remind us that science is not just data, but imagination. To listen to space-time is to change how we conceive of existence. The fact that humans, fragile beings on a small planet, can detect the collision of black holes a billion light-years away is staggering. It is a testament to curiosity and persistence, and a cultural achievement as much as a scientific one. The road to a gravitational universe. As the 21st century unfolds, the gravitational universe is coming into focus. We now have three pillars of gravitational wave astronomy: ground-based detectors, like LIGO and Virgo for stellar mass binaries, pulsar timing arrays for supermassive binaries, and soon LISA for the low-frequency regime. Each fills a different band of the gravitational spectrum, together providing a complete picture. In the near future, these pillars will be joined by third-generation detectors, by more sensitive pulsar timing networks, and by new space missions. The stochastic background will be measured. Exotic sources will be probed. Standard sirens will measure cosmic expansion to percent-level precision. The gravitational universe will not remain exotic, but will become a routine part of astrophysics, as indispensable as telescopes or satellites. Listening to the first seconds. The ultimate goal is to hear beyond the stars, into the first seconds of cosmic history. If inflation occurred, it should have generated a spectrum of gravitational waves that still vibrates across space-time. Detecting them would provide direct evidence for inflation, pinning down its energy scale and perhaps distinguishing between competing models. These relic waves would carry information from energies trillions of times higher than any particle accelerator can reach. They would tell us whether symmetry breaking in the early universe generated defects like cosmic strings, whether extra dimensions influenced expansion, and whether the Big Bang was truly singular or part of a cycle. Gravitational waves are the only messenger that can reach this epoch. Light cannot. The universe was opaque until 380,000 years after the Bang. Neutrinos cannot. Their interactions decoupled only after 1 second. But gravitational waves decoupled instantly. They carry the first heartbeat of the cosmos, waiting for instruments sensitive enough to hear. The human journey into space-time. The story of gravitational waves is also the story of human ingenuity. For a century, they were thought too faint to detect. For a century, Einstein's equations whispered their existence, while skeptics argued they were unobservable abstractions. Then thousands of scientists, engineers, and technicians built instruments so precise they could measure distortions smaller than an atomic nucleus across kilometers. This is science at its best. Theory predicting phenomena, technology rising to the challenge, observation confirming predictions, and surprise discoveries expanding the horizon. The road was long and fraught with failure, persistence prevailed. Today, gravitational waves are routine. Tomorrow, they will be indispensable. The symphony of spacetime. Black holes, neutron stars, and the ripples they create are no longer hidden. They are part of our sensory world, part of the story we tell about the cosmos. Gravitational waves have given us a new instrument with which to play the symphony of the universe. The symphony is vast. It begins with the high notes of black hole mergers, quick and sharp, like the strike of a cosmic violin. It includes the deeper tones of neutron star inspirals, resonant and complex, enriched by the glow of kilonovae. It encompasses the base of supermassive inspirals, vibrating through LISA's detectors for years. It hums with the stochastic background, the collective voice of billions of mergers. And beneath it all may lie the primordial chorus, the relic waves from the first moments of time. As we listen, we are reminded that the universe is not silent. It is alive with motion, vibration, and resonance. To understand it, we must not only look but also listen. In doing so, we have extended our senses to the fabric of reality itself.